Okay, good day, my viewers. Once again, you are welcome to today's episode of our tutorials. So, we'll be continuing from where we stopped in the last class, and today we'll be talking about the application of Newton's law of motion. In the last class, we talked about the three different laws of motion. We talked about the Newton first law, the Newton second law, and the Newton third law of motion. So, today we'll be continuing in the application of Newton's law of motion, and which is the basis for, the science, the uh, careers that we have today. Of course, different careers we have under science, we have the engineering, and so all these laws and principles and theories we are considering, they have their application in one way or the other. So, before I continue, once again, you are welcome again to our today's episode, today's session of tutorials. And for wherever you are joining us, please subscribe to our platform, like it, share it, and comment on it. Engage the comment section. You can drop your comments in the comment section. So please like, share it to as many, especially those that are writing WAEC this year and those that are writing JAMB this year. Be very, very helpful and it's very educative for them. So please like, share, and subscribe. Thank you very much. So we continue today in the tutorial section, and one of the applications we'll be looking at is in terms of the calculation base. We'll be considering the calculation aspect of some of this Newton's law of motion. So, and one of the examples I have here, one of the questions I have here says, a towing van, a towing van tows a car of mass 1,500 kilogram along a level road and accelerates at 0.8 meter per second. What is the tension in the towing string? What is the tension in the towing string? So we are giving an example here, and of course we are considering the application, which is the calculation aspect. So we have a towing van tows a car of mass 1,500 kilogram along a level road. Now, let's just assume this is a level road. I know that our roads are the best. Nigerian roads are the best. Sure. So, this is a level road. This is a level road. Yes, a smooth road. Now, a towing van. Let's assume this is the towing van. Now, that's the so this is the towing van towing a car. Assume this is a small car. So a towing now this is the towing van and this is the car. So this is the tension, the string, the rope that the towing van is using to tow the car. So and it's on a level road. Now the mass of the car is 1,500 kilogram. And the question says a towing van tows a car of mass 1,500 kilogram along a level road and accelerates at 0.8 meter per second. That is, it keeps going. It's increasing its speed gradually and its velocity gradually. So it accelerates to keep the pace and the distance and the speed. What is the tension in the towing string? That's the question. Now, what is the tension? That is, we are asked to look for the tension here, which is the force. The force, tension or force. So the question says you should look for the tension or calculate the tension of force That is the force that this towing van is using to tow this car to keep it pushing, keep pushing, keep pushing. So, and of course, for those of us that are conversant on the road, know that your towing van is always stronger and a bit, of course, bigger than the car, because one that will pull the other, one must be greater than the other. So this is just the illustrative representation, as you can see. So we have our mass to be 1,500 kilogram on a level road. This is the towing van moving this car. Maybe for whatever happened to it, they had to move it away from the road, and they are going on a level road. So now, there are two sides to this question. Like, there's another part B, but the part A says we should get the tension and the force. That's the part A, the tension and the force. So, and from our uh, last class, where we looked at the Newton's laws of motion, you could remember. So, our formulas once again: F is equal to what? FA. That is, our force is equal to mass times acceleration. So please, you can refer to our last episode that we did. So our force here is equal to our mass is 1,500 kilogram times. Now our acceleration from the question given says 0.8 meter per second square. Yes, it was given to us in the question, 0.8 meter per second square. So we have our acceleration to be 0.8 meter per second square. Now, F will give us what? 1,500 and 0.8. In case you don't have a calculator, especially for those in JAM and you are not given privilege or access to scientific calculator, of course, you will have calculator on your screen where you can calculate. But as a mathematical student, you can just work it out. 1,500 times 8 over 10 makes it easier for you. Please cancel this. Then we have 150 times 8. And that will give you what? So when you multiply 150 times 8, what will it give you? To give you 1,200, yes, kilogram meter per second square. Or, like I said in the last class, another unit for this is what? 1,200 Newton. Please take note of this, especially for those that will be writing JAMB. Your options in your JAMB question, you might not see Newton as the unit put in your answer. You might see kilogram/meter per second square. So please, either of these is correct, and you must check out for your options very well. Even for those writing WAEC too, please take note of that. So that is just a simple one of the applications of Newton's law of motion in its calculation. Very well. So now we move to another calculation, another application. Yes, another application of Newton's law of motion. Newton's first law of motion states every object or every body will continue in its present state of rest or in uniform motion except an external force acts on it, except an external force acts on it. So we're looking at another application. Yes, another application of Newton's law of motion. Now, yes, before I continue, let's look at the second aspect of this question. This is the part A. The second aspect states if the towing string, yes, suddenly breaks when the car reaches a speed of 20 meter per second. Yes, back to our formula, our diagram again. Now back to our diagram. once again. So the question says if the towing string suddenly breaks, if the towing strings suddenly breaks, so we have if the towing string suddenly breaks, and we have this, 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 this. Yes. This is the string. The string, like I made mention before. So this is the string. That is, the string means the rope that the towing van uses to pull this small car along at the back. So if this string, the second question says, if the towing string suddenly breaks, and that's why I use dotted line to represent the breaking. If it's continuous, it will just be a long straight line. So to represent that the string broke into two or into pieces, we're not told. But the question says if the towing string suddenly breaks when the car reaches a speed of 20 meter per second. So the speed given is 20 meter per second. Now calculate the distance covered. Remember this is our mass 1500 kilometer kilogram. Now calculate the distance. This is S, or at times you can have it either S or D depending. So but let's put it as S. Now calculate the distance covered by the car before it comes to rest on application of a braking force of 2000 Newton. Now the question says calculate the distance covered by the car, not by the towing van. Calculate the distance covered by the car before it comes to rest on application of a braking force of 2000 Newton. That is, the towing van, remember the string suddenly cut, and because of that, the car came to a stop with the application of the force, the brake, which is the force applied. So the force which is the brake applied is 2000 Newton. It's 2000 Newton. So what do you do? The question says you should calculate the distance that the car has covered while the towing van was moving the car. So calculate the distance. This is the towing van, this is the car. So as the towing van keeps moving, it keeps driving the car on its own. Of course, if you see them on the road, you see that there's a rope that connects the towing van and the car. So as the towing van is going, as long as the rope is connected to the car keeps moving with it. So we have to calculate the distance the car covered. Now, and how do we get it? Now remember, we've gotten our tension to be what? 1200 Newton in the previous question. That's the tension in the string. The tension in the string. Now, the force applied while putting the brake, while applying the brake, says 2000 Newton. So, and now the car was brought to rest. So, since the car was brought to rest from a speed of 20 meter per second, definitely our momentum is equal to 0. Reason being that the car was brought to rest. And what do I mean by the car was brought to rest? Momentum is mv minus mu is equal to 0. Is equal to 0. Reason because it was brought to rest. But meanwhile, this is the change in momentum. So if this is the change in momentum, so definitely our change in momentum, this is momentum, our change in momentum is equal to mv minus mu. And this will give us what? M into bracket v minus u. So m into bracket v minus u. And what would that give us? Our m is 1,500 kilogram to bracket. Now, our v, how do we know our v? How do we know our u? Now, our v is what? The final velocity. Our u is what? Initial velocity. So that will give us what? 20 minus 0. Remember, with a speed of what? 20 meter per second. A speed of 20 meter per second. So that's the speed at which the towing van is towing the car at 20 meter per second. So it has been on a constant velocity for 20 meter per second. But because of the string that broke, the car suddenly comes to a stop and comes to rest. And that gives us our u to be 0. Comes to rest. So what will be our answer? That will be 1,500 times 20, and that will give us 30,000 Newton. That will give us 30,000 Newton. So that's now back to the force, to the, yes, 30,000 kilogram per meter per second. Yes, sorry, 30 kilogram per meter per second, because that is the change in momentum. Yes, that we are looking for 30,000, because this is mass 1,500 kilogram. This is our velocity, which is meter per second. So our change in momentum will be what? 30,000 kilogram slash meter per seconds, because the unit of our velocity is meter per seconds. Now we now want to get the force now. So remember, because we want to get the time taken, we are going to S to find the distance. That's the question, to find the distance. So we want to find the distance. Now remember from F is equal to change in momentum over time. If you can remember, that is from Ft is equal to mv minus mu from our previous episode. Remember, Ft is equal to what? Mv minus mu, which is impulse, our change in momentum is equal to impulse. Impulse is equal to mv minus mu. So now to get our time taken now, t is equal to mv minus mu over f. So our time taken now will now be, remember we've gotten this, our mv minus mu is equal to what? 30,000 kilogram per meter per seconds. Our f is equal to what? 1,200 Newton that we got before. So now our t is equal to 30,000 divided by 1,200, and that gives us 0,000. Now 300 divided by 12, that gives us 25 seconds. 25 seconds. So that's the time taken during the change in momentum. Now to now calculate the deceleration. Deceleration means so our deceleration equal to minus a. Remember, the car was brought to rest. So this is acceleration. This is deceleration. So as it's going up, it keeps increasing. As it's coming down, it decreases. So this is acceleration. This is deceleration. This one keeps coming down. This one keeps going up. So our deceleration now from our formula is equal to v minus u over t, and that will give us what? 0 minus 20 over our t. Remember, is 25 seconds that we got here, and that will be minus 20 over 25, and that gives us minus 0.8 meter per second square. Minus 0.8 meter per second square. So to now determine the distance now covered by the car before coming to rest, the distance covered by the car before coming to rest, so to calculate the distance now, to determine the distance covered by the car before coming to rest, we now go back to the formula, those laws of equation. Remember, we have v is equal to u plus at, v s is equal to ut plus half at square, then v square is equal to u square plus 2as. So we look at the formula we want to use here and look at the one that we have. The parameters all complete. Remember, we have our v and we have our u. Our v is 20, our u is 0. Remember, so we have, so we can use this third law of motion. This is first law, this is second law, like the equation of motion. So we use this third one because it gives us the parameters more appropriately. So we have v square is equal to u square plus 2as. Now we are looking for s. So to look for s, we make s the subject of formula. That gives us v square minus u square is equal to 2as. And dividing both sides by 2as, 2a, 2a. So it gives us v square minus u square over 2a is equal to s. Let me put it in a more because so now v square minus u square over 2a is equal to this cancel this. Now our s is equal to v square minus u square over 2a, and that will give us here we have is 0 minus 20 square over 2 times minus 0.8. Remember, is deceleration from our question that we got. The A is deceleration because it was brought to rest. So 2 times minus 0.8 square. And S will give us what? 0 square is 0 minus this. This one will give us what? Minus 20 square minus 20 square is what? That's 400. Because minus times minus is plus. Because we're having square of this. So this is minus 400. Remember, this is minus 400 over, because this is 20 square, give us 400 over 2 times 0.8 will give us 1.6 minus 1.6. So now minus will cancel minus, minus will cancel minus. So we left with 400 over 1.6. And when you divide 400 divided by 1.6, it gives us what? 250 meters. Give us 250 meters. Please always ensure you write your unit for your final answer. Ensure you write your unit for your final answers. Please, it's very important. So our distance covered by the car when it was brought to rest is what? 250 meters. So that is the final answer for this. Now we move to another application. We move to another application of Newton's law of motion.